Hi, everyone. Thanks for coming to the March edition of our webinar series. I'm Stephen Webb. I'm a senior research scientist at Radiasoft, and this month we have with us Dr. Nathan Cook. Nathan is a senior research scientist at Radiasoft. He received his PhD in physics from Stony Brook University, where he studied advanced accelerator concepts for energetic ion beam sources. Nathan's research explores a diverse array of computational physics for accelerator systems, including modeling electron emission devices for energy applications, structured plasmas for particle beam sources, and beam plasma interactions for advanced diagnostics. Also on the call is Dr. Chris Hall, who is also a research scientist at Radiasoft. Chris will be helping us answer questions today. And today, Nathan is going to talk to us about designing novel electron emission devices with warp using the Sirepo app. So take it away, Nathan.
All right. Thank you very much, Stephen, for that nice introduction. And thanks everyone for joining the webinar. As Stephen mentioned, today I'm going to be giving a brief introduction to designing electron emission devices using warp and the partner Sirepo app, Warp VND, which is designed specifically for modeling certain classes of electrostatic devices. Before I begin the demonstration, I'm going to provide a very short presentation that gives a little bit of an overview of certain types of electron emission devices, and in particular, thermionic energy converters, which will be the focus of our demonstration. So before I get into the thermionic energy converters, I just want to provide a very brief motivation of why electron beam sources are important, what their applications are, and just a little bit about the ways in which they're used in modern technology. Electron sources have myriad applications for all sorts of basic research, industry, and medicine. And I'm highlighting a few in this slide right here. Some of the more popular or more commonly used applications in the particle accelerator community include X-ray light sources, both synchrotron and linear accelerator-based light sources, particle colliders for discovery science applications, but also you'll find electron beam sources are quite common in use for radiation therapy, as well as the production of X-rays for imaging, and also for space propulsion. And pictured in the bottom right corner of the slide is a Hall thruster. So it's a propulsion device based on the generation of an electron beam and then subsequently an ion beam that's used for satellite propulsion applications. The application that we're interested in, though, for this discussion is one of thermionic energy converters. And what a thermionic energy converter is essentially a very compact, simple heat to energy transformer. I'm sorry, heat to electricity transformer. And the principle of operation is rather straightforward. By driving an electron current between two plates, which are connected by a load, you can generate an electrical energy. And the source of the electron current is a heat source that's used to heat the left side or hot emitter in this figure, which emits thermionically electrons which cross a narrow gap and are collected by a cold collector. And so you're able to draw a fairly large electric current across this gap if you have a very high temperature for your emitter, and you're able to actually draw quite a lot of power across this device if you have a large ratio of temperatures and a large ratio of voltages across the gap. And thermionic energy converters have been in use for quite some time, more than 50 years, but they're actually becoming of great interest to quite a lot of people now because of their many advantages and because of specific specific advances in material design that are making those advantages easier to realize. And these advantages include the ability to operate with very, very high input temperatures. These can be much greater than 1000 Kelvin and even approaching 2000 Kelvin in some cases. And that makes them useful for a variety of different input heat sources because this temperature operating range extends far beyond that of a traditional steam turbine. They're also able to generate very high power densities on the order of many watts per centimeter squared, and theoretically upwards of hundreds of watts per centimeter squared, which means they can be compact and high power density devices. They feature no moving parts, which means they don't require standard maintenance the way that the blades of the turbine might. And oftentimes they can feature long lifetimes, even when operating in harsh environments. Some of the earliest applications of these devices were actually in satellite operations, as well as in desert or remote power station operations. So all of these advantages combined make thermionic energy converters a very attractive technology for modern modular power systems. However, their design is still rather quite challenging, and it imposes a certain number of unique demands on modeling tools that are used for their design. Some of these challenges that I'm highlighting and we'll discuss a little bit more today include the needs for self-consistent thermionic emission modeling. You really need to be able to capture all of the various facets of the electron emission, including the self-consistency of the emission and space charge buildup in the gap. Because these are small structures, you really need to be able to resolve with high accuracy many of the various nanoscale structures that might be used for support or for manipulation of the electron current. And lastly, you really need to accurately capture electron surface interactions, not just with the emission process, but also with the collection process of the electrons in the system. And what I'll be showing for this demonstration is that the warp code, as well as the Sirepo warp VND interface, have really been designed and improved upon to meet many of these challenges for device design. So the first challenge that I discussed is that of modeling the electron emission. And thermionic emission traditionally follows what's known as the Richardson-Dushman model. This model can be augmented for things like field enhancement, such as including the Schottky effect and various other features. But generally speaking, the Richardson-Dushman model relates the emitted current according to the temperature of the emitter. So there's a t-squared factor in the emitted current density, as well as the work function emitter, for which the current varies exponentially, and the applied electric field, which is also an exponential effect. And essentially what this means is that the emission current densities can become very, very high if there is a very high temperature of your emitter and a very low work function of your emitter. So traditionally speaking, these kinds of devices are designed to operate at high temperature, and the materials are designed to have a low work function to improve the emission current density. However, if you're looking to model these kinds of systems, it's very, very important that you correctly capture the electrostatic fields along the surface. This is really important for capturing this field enhancement effect. And it's also important that you're producing enough macro particles in your simulation to appropriately sample the distribution. Because this is the thermionic emission is a temperature dependent effect, you will generally emit a Boltzmann-like or half Maxwellian distribution, for which many, many particles lie in this extremely energetic tail of the distribution. And it's really important that you sample this portion of the distribution correctly if you're going to accurately capture the dynamics of your device. And we've chosen to focus on the modeling of these devices using the warp code. Warp is a particle and cell framework that's publicly available, open source, and it's been developed by a collaboration between Livermore and Berkeley Lab for many years now. The code features quite a large number of capabilities that are applicable to not just particle accelerator systems, but also these kinds of electrostatic devices. A few of the features that I want to highlight here that are really critical for these kinds of devices include a self-consistent solver, which factors in the space charge of your emitted electron beams and can capture things like field enhancement and various other fluctuations in the emission surface. It includes mesh refinement capabilities for improving the sampling of the field near very highly resolved or very rapidly changing surfaces. It includes cut cell features, which allow you to resolve boundary conditions that change basically at a sub-cell scale length. And then it also includes variable particle weighting for improving the particle sampling for emission algorithms, so that not all particles have to be emitted with the same weight. That allows you to get much higher particle statistics in regions of very high field enhancement or where the temperature of your emitter might be changing. Before I move on, I just want to note that for more information, you can find quite a lot of information about the warp code at the Lawrence Berkeley website, as well as recent information on some of the emission capabilities that we've improved upon in the code in my colleague's paper in the Journal of Vacuum Science and Technology. So a second challenge to modeling these devices is one of capturing the intragap dynamics of the electrons. It's not, because of the nature of these devices, there's quite a lot of complexity to optimizing how many electrons cross the gap. And in particular, the space charge of the electrons, when operating at very high current, imposes a significant challenge to maximizing the efficiency of the device. And to this end, it's intragap electrode structures are often employed to essentially accelerate or enhance the amount of current that can be drawn from this collector and actually can be carried across the gap. And so in this figure in the bottom left here, I'm showing essentially the use of a intragap electrode, which is used to essentially combat the buildup of space charge and accelerate electrons to midway through the gap, at which point the space charge is reduced significantly, and the electrons then decelerate and move as they move towards the cold collector. And it's been shown in general that for very, very high operating currents and for larger gap distances, that space charge is the limiting factor in achieving the power densities desirable for these devices. And so the use of these interstitial electrodes is critical to realizing optimum device efficiencies. Of course, you can't simply put a plate across in the middle of this device. You're very likely to block many of the electrons as they pass. So the design of this gate geometry is extremely important for improving the device design. And oftentimes these days, very complex laser cut gates are used for achieving the best performance. And so one of the features that we're highlighting in the warp code here is the ability to import STL files to describe such complex geometries. And so I'm showing as an example, a honeycomb-like mesh structure, which could be used as an interstitial electrode. This mesh structure could be designed and exported from an external code, and then imported and installed in warp, where the representation of the fields and potentials that are driven by this gate structure can be accurately represented. Third challenge I want to highlight is accounting for electron surface interactions. And just very briefly, essentially, as the electrons approach the collector, it's possible that they may not actually be simply absorbed, and in fact may reflect off of the surface of the collector. This is sort of an inverse interaction to the actual electron emission process. And the probability of reflection is a function of the electron incident energy, the surface characteristics, and the temperature of the anode. And the introduction of this reflection effect has a significant impact on the total current draw of the device and may alter the optimum device operating point. We've modified the warp code and subsequently the warp V&D interface to enable particle reflection, both from these collector surfaces and also from other internal conductors, such as these gate objects. The interplay of reflection and emission properties is really critical to understanding your device, but it also remains an ongoing area of active research. Of course, when you're trying to evaluate your devices, it's important to understand what it is that you're trying to extract from the device. And oftentimes you'll see efficiency as the quoted metric of interest. And in this case, we've defined an efficiency metric according to various loss channels within the device. I don't want to go too deep into this because our demonstration won't really touch too much on the device efficiency calculations, but I just want to note that there's more information about this model available both in publications, recent publications, as well as at the Radiosoft RS Warp repository, which is a GitHub repository that's open source and available for use and provides quite a large number of Python-based tools for running warp simulations and evaluating warp simulations. And before I begin the demonstration, I just want to touch on one more simple case study to kind of give you a intuition for what the aim is with designing one of these devices. And so I'm imagining a scenario here where we have a triode-like structure. Essentially, we have a cathode, an anode, and we're using a rectilinear gate pictured in the top right here to accelerate electrons across the gap. And so the question we might have is, where do we want to place this gate in order to optimize the performance of the device? And it turns out that it's not as trivial of a question as you might think, because the placement of the gate near the emitting surface may enhance the current by applying an additional longitudinal electric field on the surface. However, it will also introduce, it turns out, transverse electric fields shown in this picture here. These increased transverse electric fields have a tendency of increasing the transverse momentum of the electrons that are emitted, and as a result, reducing the effective transparency of the electrons. The increase in transverse momentum will cause more electrons to collide with the gate, resulting in those electrons being lost during passage across the device. So what the plot on the bottom left is showing is that, in fact, rather than, if you want to maximize total current, you may want to move the gate closer to the emitter. But if you want to maximize total transparency and therefore efficiency, you're actually going to want to move the gate farther away from the emitting surface and closer to the anode. So these are the sorts of questions that you might ask, and one of the reasons why high fidelity simulations are so important to understanding device design. So now I want to move forward with a demo. And let's see, to do that, I'm going to have to quickly stop sharing my screen, and I'll begin sharing my browser window here. Okay, so this demo begins at Sirepo.com. So if you'd like to follow along, you can simply go and open up a browser window. Sirepo works across most all common browsers, and navigate to Sirepo.com. And when you reach Sirepo.com, you'll reach this landing page, which provides a bit of information about Sirepo. And you'll see in the upper right-hand corner a list of supported codes. So Sirepo has been used quite extensively amongst the accelerator community. And so there's quite a number of codes that it supports for common accelerator type simulations. For the purposes of this demo, we're going to use the Warp VND platform. So you'll want to click on Warp VND under supported codes, and that will bring you to the landing page for the Sirepo Warp VND interface. This landing page is similar to what's in use for all other Sirepo platforms. So it should be familiar to you if you've used Sirepo for Elegant or Opal or other simulation codes. And so what you'll see is an examples folder, and you should see another import folder as well, and this import an STL command as well. In my case, I've created an extra folder. You can always organize your simulations as you'd like by creating new folders using this new folder button at the top right. So for our purposes, we're going to begin by clicking onto the examples folder here and navigating to the gridded TEC 2D opt. These blue starred files are all examples that are preloaded with Sirepo. So even if you're it's your first time user, you're still going to be able to quickly navigate to these sort of pre-designed simulations. So I've clicked here on gridded TEC 2D opt. And what's opened here is the source tab of Sirepo. So this is essentially the initial interface for you to design the simulation and take a look at the simulation geometry and basic parameters of the device. And I'm going to basically just walk you through each one of these panels really quickly and provide a little bit of insight into what the capabilities are in each case. So first, we want to take a look at this simulation grid panel. And the simulation grid panel has three basic parameters that we're specifying here. The simulation mode, which is basically the geometry of the domain. So we can specify either a 2D domain or a 3D domain. And you'll see that if you click on 3D, we actually get a new feature here, which is an additional dimensional capability of the simulation. We're going to run our simulation in 2D, but I'll briefly show that if you do create a 3D simulation, you'll see that the interface responds to that request and provides you with an additional panel in your conductor grid to show you what the simulation dimension looks like in the Y plane. And it also brings up a 3D preview capability where you can see what the entire simulation domain looks like. So we're going to click back to 2D simulation. And anytime you do make changes to one of these panels, you'll see the Save Changes button come up. So that will allow you to just quickly save those changes or cancel and go back to what you had before. The other two parameters available here are the plate spacing, which refers to the Z coordinate or longitudinal spacing between the cathode and anode, and the channel width, which is basically the transverse coordinate. So that's this coordinate here for channel width and this coordinate here for plate spacing. If you want to look at more details of editable parameters, and this goes for any of the panels, you can click on this edit button, and that will bring you to a pop-up window that has additional capabilities that can be adjusted. And this includes, in this case, the X grid points and Z grid points. This refers to the size of the mesh that we're using to resolve the domain. So you can ask for a more highly resolved mesh or a less highly resolved mesh. In this case, we're going to stick with the default values of 20 and 250 respectively. We also specify a particle Z minimum. This is essentially the position, the minimum position at which particles will be emitted by our emitter. And we choose a non-zero emission location because it helps prevent instabilities or sort of unphysical behavior of electrons if they're emitted very, very close to the surface where they may be reabsorbed. So now that we've designed our simulation grid, we're going to next take a look at the emitter and collector properties of our simulation. So first, we want to specify what the actual emission mode will be. And in this case, we want to use thermionic emission. And we're going to use an electron beam as our species. Electrons are really the only available option right now with this configuration. We can then specify the cathode temperature, the anode voltage. So in this case, this is how much voltage is being applied across the gap by the anode. And then we can specify cathode and anode material properties. And this includes work function in electron volts, and as well as particle reflection. So this is again referring to the surface property of particle interactions that I discussed before. And you'll have two different options, diffuse and specular reflection to choose from. Specular reflection is exactly what it sounds like. Particles will be reflected with equal and opposite momentum from the point of contact with the surface, whereas diffuse reflection will essentially recharacterize the momentum of the particles at random. We're not going to use particle reflection for this example, but this does show you that you could in fact apply this for each one of these surfaces. And then if we click on the pencil icon here, the edit button, we'll see there's one more parameter. That's the beam X radius. This is essentially an emission limiter that you can place in the simulation that will change the effective region of emission. In this case, we'd like to emit entirely from the whole domain. A big reason for this is that we're trying to essentially emulate a much larger device than what we have in our simulation domain. So right now, what we're seeing is we have 100 nanometer transverse size of our simulation, but in reality, what we'd like is for our device to be much, much larger than that transversely. And so we're using periodic boundary conditions on our simulation to essentially emulate an infinitely wide emission plane, but we're only simulating a very small slice of that. So we'd like to emit from the entire region because in reality, our device is going to be much larger than this 100 nanometers. So now that we specified the parameters for our emitter and collector, we can explore the grid or conductor configuration of our simulation domain, and then play around with adding in internal conductors to use as an interstitial grid. So we can see this, the conductor grid provides a basic layout of our structure. And we can essentially see that there, in addition to the emitter and collector, there are these small orange nodes on our within our simulation. These are essentially grid objects. So if I mouse over, you'll see a tooltip pop up that says grid. And if we look in this conductor types window here, we'll see the grid object is well defined and all of the various parameters are provided. So I'm going to click edit on this grid object, and it will show me that this grid object is a box conductor. It has a specific voltage, in this case 16 volts that's been applied to it. It has a length of roughly 50 nanometers, width of 2 nanometers, and a depth in Y of 10 nanometers. This is, of course, ignorable for the 2D simulation. It's defined as a conductor, and particle reflection is turned off, although you could change it if you'd like. And you can, of course, specify a color as well if you're trying to coordinate different types of conductors by color. And so we have 5 grid objects in our domain. All 5 of them are listed by their position, and all 5 share the same properties. So they share the same size and the same voltage. If we wanted to, we could add a new grid capability, a new grid object, simply by clicking on grid until a blue shadow appears of this grid button. And then we could drag it and drop it into the simulation domain. And then we'll see that at the bottom of our list, a new object has appeared. So now we've added a 6th grid object, and we can move that around with our mouse, or we can click edit here and make changes to the location of the grid. So if I want to move the grid, I can make small changes to put it exactly where I'd like. So this is a nice feature for sort of playing around and exploring with different locations of interstitial electrode objects. If you want to get rid of the grid object, you can remove it using this button, this X button here, or you can hold it and simply drag it off the screen, and a little prompt will pop up that will ask you if you would like to delete the grid conductor, which we will do. If you'd like to define a new conductor type, such as to say a conductor that has a different spatial extent or configuration from the grid object, then you can click on this new conductor type button here, and you can define, grid 2. And then you can specify a voltage, a length, a width, and you can even specify it to not be a conductor. You can make it a dielectric and specify a relative permittivity for the object as well. And that will also be factored into the electrostatic solve for warp. And then you can give it a different color, save changes, and this grid 2 object will now appear in your conductor types tab. If you were to say have many of these objects and the list becomes extremely long, you can collapse each individual list so that you could get a quick bird's eye view of all the different conductor objects you have. So if I did want to add this grid 2, again, I could simply drag and drop items until I have them in the arrangement that I'd like. So I'm going to remove these for the purposes of the demo, but that hopefully gives you an idea of the sort of interactivity of this. So now that I've designed a basic simulation, I'd like to take a look briefly at what the field structure of the simulation is and ensure that the device is looking essentially, producing the fields that I'd like it to produce. And so to do that, we have 2 different field comparison reports. And in order to reproduce those, we click on Start Simulation in the Field Calculation Status panel. That will run a very brief simulation here, which will reproduce 2 reports here, a field comparison report, and then a field report, which provides electrostatic potential information. So the field comparison report by default will show a line out of the EZ component of the electric field and running along the Z axis. And it will show 3 separate lines which correspond to different X locations or different transverse locations. And you'll see that they're color coded red, green, and blue. If we scroll back up to our conductor grid, we'll see that we have red, green, and blue tabs here on the interface. And those can be manipulated again by your mouse to change the effective location. And if we scroll back to our field comparison report, we'll see that these locations have again changed. We can also, if we'd like, change from plotting EZ to plotting EX. And not only that, we'll be able to see, again, specifically what the positions of each of these lines are. And so I've changed now to plotting the X component of the electric field. And if we scroll up, we can see here the 3 locations, red, green, and blue, at which we're producing these lineouts. And so we can see the variation in the transverse fields as a function of different Z locations very easily. I'm now going to demonstrate this field report panel below, which shows a picture of the electric field, electric potential across the domain. Again, in this case, it's looking at the longitudinal versus X plane. And so we can see that the potential peaks at 16 volts, which corresponds to the potential that we've applied to our electrodes, and it peaks slightly before 5 microns, which is the location of the electrode, the plane of the electrodes across the device. So what we see here is very much in line with what we'd expect based on our simulation configuration. So now that we've actually produced this configuration, we'd like to actually simulate some particles. To do that, we're going to click on the Visualization tab in the upper right-hand corner, and that will bring us to a visualization window. And if you haven't already run the simulation, you're only going to see the simulation status panel in the upper left-hand corner. And the simulation status panel will basically provide a very small amount of information and provide a few options for you prior to starting your simulation. So first, it will provide this electron gun mode option. That's essentially an iterative electrostatic solver that can be used in Warp to enhance the speed of your output. In this case, this is already a fairly fast simulation, so we're not going to use that, but it's a nice feature to explore. And then we have a sub box here that provides a little bit of information about the expected dynamics of the electrons. So first, it will give you an expected time of flight. This is based on the potential across the gap, as well as the thermal energy of the electrons, and a corresponding number of time steps that will take for your simulation. So that gives you sort of a sense of how long you need to run for to see current saturating in the gap. And then it will also tell you an expected fraction of electrons that will cross the gap. In this case, it's just looking again at the potential between the electrode and anode. It doesn't factor in the potential of the interstitial electrodes that you may add. So in this case, because the potential at the cathode is higher than at the anode, we're expecting all electrons to cross the gap. But if we had reconfigured the anode to sort of repel electrons, then that fraction could get smaller. And then lastly, we can specify the number of simulation steps. This is quite useful for changing, of course, the duration of the simulation and how long you want to run for. There are a few more parameters you can specify up here. If you click on the edit button, one is trace period. That's basically how often, for one of our particle trace diagnostics, how often the trajectories of the particles will be updated, as well as a particles per step number. That's essentially how many macro particles will be emitted at each step to represent the emission from the emitter surface. That's right now a fixed parameter at 200, so we're just going to leave it at that. So to run your simulation, you can simply click the Start Simulation button. As the simulation runs, you'll see the windows. This screen will become populated by additional windows showing certain diagnostics that are updated concurrently with the simulation, and those are updated roughly every few hundred steps. So we'll see two particular animations. One is the current animation. That'll show you essentially what the current across the gap is at any given step in the middle of the simulation. And the current in the simulation is represented by this blue line. And for context, the orange line represents the Richardson-Dushman analytically calculated current. So we can see that the emitted current for the first half of the domain is very well aligned with the expected Richardson-Dushman value. And then roughly at halfway through the domain, there's a slight dip in the current. And that dip in the current is related to electrons being caught or captured by the electrodes. So essentially they're colliding with the electrode and being removed from the simulation domain. So there is a very slight dip in current because those electrodes are not transparent to the electron propagation. You also see this field animation that is produced. The field animation will basically represent any change in the potential across the gap that happens dynamically owing to the amount of current moving across the gap. In this case, the current isn't at the space charge limit, so there's not going to be a significant change in this potential. But you can certainly walk through these plots and see if there is going to be a change on your own, or if you change the emission temperature, you might be able to see some interesting behavior here. With each of these animations, you can essentially step through the current using these back and forth buttons, and then you can rewind to the very beginning. You can also play them as a video. So they're useful for understanding the dynamics of the simulation from a very top level. Now I want to highlight these next two diagnostics, which pop up at the end of the simulation. So once the simulation's been completed, the one on the bottom left here is the particle trace diagnostic. This shows a sampling of different particle traces crossing the simulation plane. These are done using tracer particles, so they don't actually deposit on the grid, which means that their motion is going to be emitted. They're going to be emitted essentially parallel from the emitter, and they're not really going to interact with other particles within the simulation domain. But what they do is they basically trace out variations in the potential or electric field that might be induced in the simulation, either by the current that's crossing the gap or by the positioning of electrodes. So here we can see that in some cases, some particles are being captured or lost at the electrodes. Others are passing the electrodes and then being bent or curved. If you want to manipulate this plot more, you can actually change the number of particles that are rendered to increase the density of traces that you're seeing. And on the right, we have an impact density diagram. This is basically capturing the density of particles as they collide with different surfaces within the domain. In this case, we have most of the particles reaching the collector. So this is obviously why the yellow bar here is why this region is mostly yellow. But we do have some particles being captured on the actual electrodes. And again, you can change the color here. Some of you might be seeing a different color map. The cool warm, I believe, is the default. So in this case, red would mean many particles being impacted, and blue would be few particles being impacted. So now that I've shown a basic simulation, I want to explore some optimization opportunities that are presented by the interface. And to do that, we'll click on the optimization tab in the upper right-hand corner. And that will bring us to this new window, which will provide us with quite a lot of information about potential optimization that can be run. And so the most important of these is the optimization fields panel. And that's where you can design both the inputs to your optimization and any constraints on the optimization as well. So as far as bounds go, what fields we're going to actually optimize and what their constraints will be, this is pre-populated with two particular fields, grid number 1 center Z value and grid voltage. And these two parameters are taken from our source tab. So if we move back to our source tab and we look at the parameters for grid object number 1, we see the center Z parameter here, and we see this cogwheel has been is blue, it's shaded in. And if you mouse over it, you'll see a tooltip that says optimization settings. So this is the parameter that's being chosen for optimization. And then if we look at the edit for the basic grid object, we'll see that the grid voltage is also selected for optimization. And of course, you can go through and select other fields for optimization if you'd like. And you can create quite a complex array of inputs to the optimization, but for our purposes, we're just going to consider these two. So I'm returning to the optimization tab, and I can see that I have these two options selected. I also see a minimum and maximum value of each. So in this case, we're going to be varying the center position, the Z position of this grid object number 1 between 1 and 9 microns. And we're going to be varying the voltage on this object between 1 and 5 volts. Next, I want to define some constraints. And in particular, I'd like to think of this grid object as being fully connected. So each one of the grid objects will move together. And so in this case, I'm defining a constraint between those two objects, which basically specifies that grid number 1 will move with grid number 2, grid number 1 will move with grid number 3, and so on through all 5 objects. So each one of these objects will move together. And of course, you can add or change different kinds of these constraints as you'd like through the interface. And we're going to be choosing as our objective function the transparency. So we're going to be trying to maximize the amount of electrons that can cross the gap. And for more information, if we click on this edit panel, we'll be provided with information about the actual simulation and optimization parameters. We have a tolerance, so that's the value of the variation in the optimization objective function that we're trying to reach. We'll see a time limit for each run. We'll see a number of continuous field divisions. So that's essentially how many times they'll subdivide the region of interest for the optimization fields. So in this case, the Z position will be divided into 7 segments, and the voltage will be divided into 7 segments as well. And then we'll see some information on this number of simulation steps that will be run for actually evaluating the objective function. So we have an initial number of simulation steps that will be run to generate a steady state in the device. And then we'll have a number of steps between tolerance checks. So this is essentially every 125 steps after 500 steps, the optimization objective function will be evaluated and the optimizer will decide whether to continue. Having specified all of these features, we're going to start a new simulation. And when we start the new simulation in the optimization status panel, we'll see an update that the simulation is running. And very soon we'll see information about the current simulation that's being run. So we'll say running simulation 1, it will give us the parameters that it's using. So it's using a value of 1 for the Z position and a value of 1 for the voltage. And so this optimizer is designed to use a simplex type method, but it's been modified to first check the bounds. So it's going to check each one of the pairs of boundary conditions. So it'll check the low ends of the bounds, the upper ends of the bounds, and then the cross parameters of the bounds first. So you know that the first few simulations will be checking those and aren't going to be actually doing significant amounts of optimization. As the simulation progresses, you'll see updates to the number of steps that have been run, what the result of the objective function is, and various other information about the simulation. And once at least one simulation has been completed, you'll see an additional panel pop up here. While we're waiting for that panel to pop up, I just want to provide a little bit more information about more generic Sirepo features that are available that I haven't yet shown. The first of which is, I think, one of the most interesting features of the Sirepo interface, which is that you can share these simulations through a link. So if you look at the top panel, or that's the sort of top bar on this interface, and click the link button next to the name, you'll see a link to the simulation. And if you copy this link and send it to someone, they can actually open this exact simulation or generate a copy of that simulation in their browser. So it's actually quite a useful way of sharing information, either like, facets from a cool simulation or other kinds of results that you might want to share, or if you have questions about something. It's just a really good way to be able to quickly share a simulation configuration with someone. Another way of sharing the simulation, or more ways of sharing the simulation, I should say, are available in this cogwheel drop-down menu on the top right of the interface. And so there's 2 ways to download the Python or the full source of the simulation. One is to export it as a zip, and one is to download a sequence of Python and JSON files. Because Sirepo is an open source platform, and actually you can find the full source code available on GitHub. All of the code is maintained and available for sharing and download. And so if you want to see what the Python code is doing underneath the hood, you can download that and play around with it. Radiosoft also hosts a Jupyter server that's available for public use. And so you could even try downloading the Python source and running it on our Jupyter server. The Jupyter server hosts a number of Docker containers that come preloaded with all of this software. So it's very easy to get up and running with something that you've already sort of templated in Sirepo. And then you can kind of iterate or create your own analysis tools or write other Python scripts to use Warp to build off your initial simulation. For an example simulation, such as the gridded TEC one that I'm showing right now, if you made some changes and you're unhappy with them, you can also use this menu here to discard those changes and return the simulation to a sort of fresh version of the example. So now that we've given this optimization a little bit of time to run, I just want to quickly point out this optimization path diagnostic here. So this provides essentially a history of the simulation optimization that's color coordinated by the effective output of your objective function. So you can see that, as I mentioned before, it tested all of the bounds first. Those are these first 4 dots. And if you click on one of these dots, you'll see the information about the simulation displayed. So you'll see the number of steps that were taken, the amount of time that it took to run, and what the result was for the objective function, as well as the tolerance that was reached. And so this is an interesting way of exploring, why did it choose to go to this position, or what's interesting about this set of configurations, and you can get immediate information and feedback on whether that's a good operating point or not. And something that we can immediately see in this case is that the optimizer has found very quickly that higher grid voltages improve the transparency. So you can immediately see that there's a 10% or more improvement in the transparency of our device simply by increasing the voltage on the grid. And so that was sort of the first thing that it determined. And now it's looking to find what's the right Z position of the grid. So now it's jumping around between different Z values on the grid. And if you want to see where the optimizer is currently, you can find this unfilled in white circle here. That's the run that's being currently done, and that matches the information being provided in the panel above. So before I finish this demonstration, and while this optimizer continues to run, I want to highlight one more feature of the Sirepo interface, which I discussed during my initial presentation. And that is the ability to import STL files. And so I'm going to open in a new tab here, the simulation landing page again. And I'm just going to provide a quick demonstration of how to import an STL file if you want to use that STL file to describe your electrode. So you can choose import STL file, and that will allow you to upload something from your own computer. Click import file, and that will generate a new simulation pre-selected for 3D operation with a grid or lattice gate installed. So in this case, I've chosen an STL file that corresponds to a rectilinear grid, essentially a meshed gate. And the gate has been placed at 3.5 microns in the domain. If I click on this layout button, I can see the location of it. I can see information about the gate object here, and I can edit it to say, give it a voltage. By default, it's given 0 voltage, but I will give it a non-zero voltage. And then you can run a quick field calculation as well, and show essentially what the impact of including this gate in the domain is. So I think this is a really interesting feature, because again, you're often trying to understand how your device might respond to a different kind of electrode structure, and that electrode structure might not be well described by a simple box conductor. And our new conductor type features here only support rectangular objects right now. So if you want to use a non-rectangular box-like conductor, your best bet is to specify an STL file, or export a geometry to an STL file and then import it into Warp. Warp itself does support other types of geometries. So if you get comfortable enough with the code, you can actually go into the Python and load different types of geometries yourself. But this is sort of a nice way of taking a complex geometry and quickly importing it into the code. So I guess while I'm waiting for this field calculation to complete, I can answer some questions, or Stephen, if you have questions you'd like to pitch. I guess Chris has already volunteered to answer a few of these.
Yeah, sure. So thanks for the presentation, Nathan. We do have a couple questions. Alex Friedman asked 2 questions. One of them was if electrons scatter off the gate. Chris already gave a quick answer to that. The other question that he asked is, could you have made the simulation domain, say, half as tall and obtain the same results, I assume in the 2D grid?
Yeah, can you repeat the last question, Stephen?
Yeah, so the second question was, could you have made the simulation domain half as tall and obtained the same results? I assume with the
Yes.
2D.
Yes, so you can vary this transverse domain size quite significantly and obtain effectively equivalent results because it's essentially because there's periodic boundary conditions on the domain. You know, the code will essentially it operates as if the same emission current density is happening outside of the domain, right, to the left or to the above and below it. So you can definitely reduce the domain size. And in our case, I think it's fairly trivial. So if I return to this this simulation and I look at the source, right, you could hypothetically reduce the entire domain down to a single gate object because this is already a tiled periodic system. So it really just comes down to what the periodicity of your gate structure is. I just found it more interesting to include more of these items just to make it look a little bit more realistic.
And Alex just asked, a follow-up question is, would that have been faster to run?
So yes, in general, I think so right now we're running all of these run natively on a single processor. So you're not getting an advantage for going to an MPI parallelism. So there's no domain decomposition here. So I think that would be mostly in most cases, it would be faster because this is a V-cycle multi-grid solver that Warp's using to obtain the fields. If the domain is extremely asymmetric, you're not doing yourself any favors for runtime. It takes a little bit longer in the V-cycle to achieve the cycle wants to find a point in the solve where you have equal dimensions. So you're not getting perfect speed ups by reducing the domain size in half, just because the asymmetry of the domain is not something the solver likes, but it would make it a little faster.
All right, great. Thanks, Nathan. So Michael Campanelle asked a question. I'm wondering, for offsetting the space charge effect, how is inserting a mesh in the gap advantageous over moving the anode closer to the cathode?
Yes. So in general, it's not advantageous. In theory, it's not advantageous. In practice, it's very difficult to make these gaps much smaller than, say, 50 microns. And a lot of that has to do with just maintaining the structural integrity of the device, because the temperature differential between the emitter and collector may be on the order of 700, 800, or 1,000 Kelvin. If you have, say, a emitter at 1,500 degrees, your collector may be at 700 or 800 degrees, if not less. And there's definitely a lot of challenges in simply making sure that the gap distance is maintained very regularly across that structure. And so oftentimes what they use is a combination of supporting structures, basically small scale cylinders that are made of some kind of insulating material that actually connect the emitter and collector. And then they'll use an additional set of electrodes connected to those cylinders to accelerate particles to compensate for space charge. If you can make the gap small enough, then in principle, you won't have to worry about space charge. But in practice, it's not something that's done very commonly. I think there are a lot of modern designs that are aiming to do that, but I don't think they're fully mature yet.
Thanks, Nathan. All right. So we had one last question from Alistair Tenkate. I hope I pronounced his name correctly. In your early slides, you seem to show nanoscale structures on the cathode as enhanced emission sites. Can those easily be added to the gridded TEC example?
So not at the moment. That is a feature that would be nice to add, but we don't have that capability in the interface right now. We do have that capability in Warp, and that is something that there is code available to do that in RS Warp as well. And you're certainly welcome to reach out to me if you have more questions about that. That's a feature that's sort of a newer development. And what it really requires is a a different kind of emission algorithm, which weights the emission based on the field. And that algorithm is not in place for this example because it's just a little bit more picky. And so it's kind of layered on top of Warp's basic emission features.
Great. Thanks, Nathan. So are there any other questions? All right. So nobody's posting any new questions. I'm going to post a link to our YouTube channel once again in the chat. You'll be able to find this and all of our other webinars there. We'll be posting this webinar in about 2 weeks, and you will get an email since you registered about a week from now with early access to the webinar video if you want to revisit this. So with that, I'd like to thank our panelists, Nathan and Chris, and I'd like to thank everybody for attending the webinar. Hope everybody has a great afternoon. Thank you.
Thanks, everyone.